Thank you, and welcome everyone to Building Invincible Applications with Temporal and Astra DB. In this short webinar, Loren and I are going to take you through how to use Temporal with Astra DB and kind of how to build things under that paradigm of durable execution. So I'm Aaron Pletz. I'm a developer advocate with DataStax. I am the host of the Apache Cassandra Corner podcast that actually Loren has been a guest on recently. I was a 3-time Cassandra MVP back when we still did that, and I've written a couple of books on distributed databases. Loren, why don't you tell us a little about yourself?
Hi, folks. My name is Loren Sands-Ramshaw, and I'm a developer advocate at Temporal. And formerly, I was an engineer on our language runtime team, working on our node runtime. I'm a system design enthusiast, developer experience nut, a longtime open source maintainer, and author of a book called The GraphQL Guide.
Excellent. So here's our agenda for today. Obviously, we're going to finish our little intro here and then move on to talking, cloud native development with DataStax. We'll talk a little bit about, hey, what does Temporal bring to the table and how does it really help in that situation? And then we'll talk about the joint value of DataStax and Temporal together. And then finally, we'll open it up for some Q&A at the end. All right, so a little bit about DataStax. We are actually known as the company that's behind the Apache Cassandra project. We've been active in the community since 2010. Fast forward, and we have a database as a service known as Astra DB, which is built on Apache Cassandra. Our Astra platform also has a streaming service, which is a message broker and event processor built on Apache Pulsar. And then recently we've acquired a company called Cassandra, which is kind of helping us build for the future a little with real-time AI ML applications going forward. And really what this shows is that DataStax really has more than a decade's worth of real-time innovation that's bringing us toward this toward this advent of real-time AI. So of course, the impact of real time, 71% of organizations that were surveyed, indicated that real-time data is a key factor in growing revenue. And that really putting that strategic focus on real-time data, has that transformative impact that they need on revenue. Ultimately, though, what the DataStax Astra platform does is it improves the cloud native developer experience from the data store side. You can quickly spin up highly scalable resources. We can deploy multi-region or even multi-cloud, which is good for getting your data to where your customers are. We offer auto scaling, so as your workload goes up, your resources will track along with it to make sure that you're not dropping any requests. And of course, all this is done, hands-free, no operations. So there's nothing for you to worry about as a developer in this case. And ultimately, what this allows us to do is build fast, scale without limits, and really, deliver that world-class level of economics of data at scale. All right. Well, Loren, why don't you tell us a little bit about Temporal?
Sure. From a high level, Temporal is a platform that enables your engineering org to have and maintain fast velocity of development. So we broke up the monolith into microservices in order for each team to be able to deploy separately. But when we did that, we introduced a lot of new problems that we didn't have before when all of our updates went through a single database with asset transactions. When we are in a microservice world, we have to take into account the possibility that any downstream service we call might be down. And we also have separate data stores that we need to maintain consistent state through. So Temporal is a platform that takes care of a lot of these distributed system concerns for you, so that your developers don't get bogged down by these new microservice concerns, and they are able to maintain their developer experience and development velocity. Speaking to what that is on a more practical level, in the next slide, Temporal is a platform that provides durable execution. So what is durable execution? Durable execution is running code in a way that that guarantees it to complete running. And you might think, what's the big deal? Of course, code completes running. That's how it works. It goes line by line until the end of the function, and then it returns, and then it's complete. But there are a lot of situations in which your process dies. So it could crash. You divide it by 0 somewhere. It could get killed by the OS. Maybe you're out of memory. It could get shut down as part of a code redeploy. So there are lots of cases in which your data center could lose power. So it's always possible that your process will fail, and if you do, you lose all the context of what you're trying to do, unless you've saved state to the database. And the paradigm we're used to is volatile execution, is programming when you don't know if your process will always be around and whether execution will stop between 2 statements in your program. And so when we have mission critical workloads like financial transactions or most business processes, we checkpoint state in order to make sure that we can recover in the case of a crash. So we write to the database, okay, we just did this step. Okay, we just did this step, etc. And then we have like a worker pool that checks the database saying, okay, are there any things that got stuck on a step and didn't complete? And then if yes, I will take that task and go to the right place in the state machine and progress to the next state. And that's a lot of code to write and maintain and debug. So there are a lot of things we're used to doing given our traditional paradigm of volatile execution, where this process can die at any time. And and the durable execution is sort of a new programming primitive you can use that makes it so you don't have to be concerned with a lot of the things we are concerned about in our current paradigm. And it also opens up a lot of new possibilities. So with durable execution, the execution system is sort of driving your code and deciding what gets run when. And one major benefit to that is it's doing the calling of any traditional volatile code that you have in your durable code. And what it does is it calls the function, and if it fails, then it has automatic retries with exponential backoff, and that's persisted and reliable, and it also has timeouts to fail things that take too long. So it can have automatic retries of anything that might fail, like downstream service being down, or unable to reach the database, or unable to reach a third-party service. You can also sleep for 30 days or an arbitrary length of time. And traditionally, this isn't something you're able to do because you don't have faith that the process will be around in 30 days. And you also, you don't want to take up resources. So like if it was doing sleep 30 days and that took a thread, then soon I'd eat up all the threads and wouldn't be able to handle any more requests. With durable execution, sleeping for a long time is guaranteed to work. So durable execution is sort of process independent. It's going to continue running on a new process if this process stops. And when it continues running, it will continue running from the next step of the code with all local variables and call stack and threads intact. Furthermore, the system takes advantage of the fact that it can continue running on a new process by not taking up resources during the sleep. So your function can call sleep, and the system will release the threads. And in 30 days, when the the timer goes off from in the database, it'll replay the function to the right place so that you're not taking up resources during that time. Another new possibility that durable execution opens up is sending RPCs to your function. So the function might be running for an indefinite period of time, and you might want to get information about its state, about what it's been doing. You also might want to send further instructions to it besides just the arguments that you passed when you started it. So durable execution systems support sending and receiving RPCs. You can also do forever functions. So you can have a function that never ends, that lasts forever. For instance, one function per user that models the user account or models their a loyalty program. And we'll see an example of that later. And finally, with functions that can run forever and can receive RPCs, you also don't need a database in many cases. You can just use your local variables. So if I have a local variable in my durable function and I have an RPC that says like get fetch value of this variable, like fetch foo, then I don't need to save foo to the database because we can trust that this function will always be running and always have an accurate value in foo. So I can just send the RPC get foo. So here's an example of sleeping for 30 days with a subscription. So we have a durable function subscription that takes a user object and an amount to charge them. We start out with canceled false. We have an RPC handler for the cancel RPC. And when that's called, we do the inline function, which is sets cancel to true, sends an email to the user saying their subscription has been canceled. And then while not canceled, the function charges the user and then sleeps for 30 days. And the sleep is the built-in function of the platform that automatically sets a timer in the database and will reliably go off. And then send, email, and charge are both volatile executions. So traditional functions that might fail because they talk to SES for sending email or Stripe for the charging, and those might be down. So this is it looks like I'm directly calling them, and it feels like that in the worker SDK that we have. But in actuality, it's going on a separate queue that might be picked up by this worker or another worker, and it automatically has a retries with exponential backoff. So here's an example of a forever function. It's a durable function called loyalty program that takes in a user object. So whenever a new user signs up for our service, we'll start this function, and we start out with 0 points, and we have 2 RPCs. The first RPC is the notify purchase RPC. Whenever the user makes a purchase, we call this and we give it the purchase info, and we take the total amount that they paid and add to the points some amount. And once the points get to a certain threshold, we send the user a coupon or notify them that they have these new member benefits. And you can have arbitrary logic in there. This is just a very simple example. And then we also have a get points RPC handler that just returns the local variable points, the integer. So if your user has a user profile in the web app or your mobile app, you can do this query to get the number of points to display to the user. And at the end, we do await promise that never resolves because we don't want this function to reach the end of the we don't want execution to reach the end of the function and return because we want it to run forever. So really, this function, the only purpose of it is to have that local variable and to have those 2 handlers. There are a number of systems that provide durable execution that will run your code for you in this way. And I work for Temporal, the one at the end. And in 2012, our co-founders launched Amazon Simple Workflow Service, which is still an AWS offering. One of them went to Microsoft to create Durable Task Framework, which is another durable execution system, and that was adopted by Durable Functions. And they came back together at Uber and built Cadence starting in 2016, and that became very popular both in Uber and outside. And Uber is still using it for hundreds of use cases internally in Uber engineering. And then they both left in 2019 to start Temporal. And we have been working on improving the open source project a lot, and we are now 130 people working on it full time. We have a lot of happy users, including Stripe, Netflix, Box, Coinbase, and Datadog.
Okay, well, thanks, Loren. So now let's explore a little bit about the the joint value of using DataStax, Astra, and Temporal together. Really, what this does is kind of opens us up to building a new class of distributed real-time applications that are cloud native. They don't have vendor lock-in. You got your real-time access to data. You get your time-sensitive insights from that, and it's globally distributed. Kind of like I mentioned before about putting your data where your users are. These applications kind of they make it so that the user application doesn't have to like jump across the ocean to get to some faraway data center. It can go to a local data center and serve that just fine. Loren, what can you add from a temporal point of view on this?
Yeah, Temporal is definitely cloud native in that we were designed to be run in the cloud, and we also don't have vendor lock-in in that all of our software is open source, MIT licensed, and you can run it on any cloud. So unlike AWS SWF, Simple Workflow Service, or Azure Durable Functions, it's not tied to a single cloud. So you can run our open source cluster and use our SDK on any cloud. Also, one thing when I think of cloud native is using microservices, and while Temporal is certainly has benefits that you can use in a monolith, it really shines in microservices and simplifying the coordination between microservices and different data stores, and sort of acting as your microservice orchestrator. For globally distributed, our open source cluster supports cross-region replication and failover, and we're also working on adding that to our cloud service, our cloud version of the server. And then for real time, we so I guess we persist every step of the program. So traditionally, we are not for latency sensitive applications, but and certainly still for like if you're counting milliseconds and you're doing like a real-time game, we're not a good fit. But if you're need response times on the order of hundreds of milliseconds, we can do that. And we also have a new feature called Update that's right now in alpha, that and you can use it with our Go SDK that has response times in the order of tens of milliseconds for more latency sensitive use cases.
Oh, excellent. So, when I start thinking about some of this, I could see that there's a question that comes in right off the bat, and that in with DataStax and Temporal working together, it's like, what problems do we solve for developers? And I guess when I think about that, and it's like the first thing that comes to mind really is about when you're building distributed systems, you always have to take things like fault tolerance. I mean, that's first and foremost, on the first and foremost that comes to mind. So you start thinking about, well, hey, I need a database that can survive, network partitions, that has that fault tolerance, as well as a code execution platform that can also survive, some unexpected events that you might find out there. So what do you think?
Right. So our open source server, the cluster of services and databases that implement the durable execution or the workflow engine is horizontally scalable and fault tolerant. Each piece of it, each service and data store can go down, and when it comes back up, it'll come back into a consistent state, which is why we can guarantee that your functions will always continue running and always represent the most recent state.
We start looking at too, certain developer requirements of, not just like, high availability and durability, but, also things like, that increase needing that increased reliability and helping them deal with complexity. I like to think that DataStax Astra solves those things of providing reliability and decreasing complexity by just taking that back end infra layer kind of out of their hands. You know what I mean? So that they don't have to operate on the cluster and on the database themselves. That it's just kind of there. It's kind of in an always on scenario.
So reliability is definitely our best selling point, and we like to call it durable execution, like writing fault oblivious code, where you don't have to worry about process being down or network being down. It just you don't have to care about it. It seamlessly continues execution or retrying whenever the process or the network is back up. And then to the complexity point, that's definitely what we're here for is improving developer experience and making especially service-oriented architecture less complex to build on. And we really see our value in reducing the complexity of programming backend systems in general.
Well, excellent. So, another question that comes up too is, how could we achieve something like this? What does that implementation look like, or hosting of it look like? I can tell you that that from the DataStax side, you could go the route of building up like your own Cassandra cluster as well, if you wanted to host your own and kind of operate it yourself, or using the kind of the database as a service cloud native approach. You could go that way as well. And then again, kind of to the points we've been making recently, is to not have to care about it. So how does Temporal work like that in terms of implementation and hosting?
Sure. So I guess there are three parts of a temporal application. There's the client, the server, and the worker. And the client and worker both talk to the server. And the server is an open source cluster, the services and data stores. And then the client and the worker both use our open source SDK. And the client tells the server, okay, start this durable function, or send this RPC to it, or stop it. And then the worker has your code, has your durable functions and also your volatile functions, which we call workflows and activities. And it is asking the server for tasks like, okay, start running this function, or okay, deliver to this function an RPC, or start this volatile function. And then it runs that code, and then it reports the result back to the server. So the server is keeping the state of the program in the database, and the worker is running your code. And in terms of how to implement it, you're writing your durable functions and using our SDKs, and we have lots of documentation about those. And then in terms of where you're hosting it, the client can be anywhere. It can be in a serverless function or anywhere in your backend. And the worker it needs to be a long-running process. So you could host that on ECS or render, fly.io, things like that. And you can scale them up if you need to, if you have higher load. And you have metrics both from the worker and from the server that can help inform when you need to scale up. And then the cluster we have is open source. You can host it anywhere, ideally near network distance to the worker. And then we also have a cloud version of the server. So the cloud version is hosted namespace as a service. So namespaces are like our unit of isolation. And the pitch is we can, it takes expertise to host the cluster well, especially at higher scales. And we're the experts, and we can save you time by doing it for you.
Okay. So now, let's say that we're using Astra DB with Temporal. What can you say about getting things to work at like a better or a bigger scale? I can say that like from a DataStax standpoint, we have that auto scaling aspect, so that when your workload starts trending up, that your resources also increase to match that. That way you're not going to see any operational timeouts or anything like that. What can you tell us about Temporal in that sense?
Sure. So the server component has a database, and we support Postgres, MySQL, SQLite, and Cassandra.
Mhm.
And the limiting factor on how high you can scale the server component is the database. And specifically, it's a very write-heavy workload because we are writing to the database every step that your program takes. And as you start using durable functions for more and more of your backend code, that can get to be a very high write load. So the general recommendation we say is MySQL and Postgres work fine up to 1,500 actions per second.
Mhm.
And an action could be like starting a durable function or sending it an RPC. And once you go beyond 1,500 actions per second, then we recommend using Cassandra for just being able to achieve a higher write load.
So now when we're looking at, again, like Temporal and Astra DB, Loren, what kind of like range of use cases are we looking at here for both of those together?
Yeah, so I guess there's two ways to think about Temporal plus Astra. We can use Astra to power Temporal server. You can also have an application that uses Astra and think about how and when to add Temporal. And that sort of splits off into two, like when do I use Temporal in general and when specifically with Cassandra. And I think for the latter, if you're ever needing to do a transaction between across partitions or across clusters in Cassandra, then doing a saga with a temporal durable function would be the best developer experience and a reliable way to do that. And similarly, if you are needing to do an eventually consistent transaction between a Cassandra database and another database in your backend, then a saga with Temporal would be a great use case.
All right. So, hey, in the next little bit of time that we've got here, let's go through some questions that have come through. I suppose I could start by taking this one. And the question is, how does DataStax Astra support real-time data and applications in multiple geographic areas? And the answer to this is that of course, DataStax Astra DB is built on Apache Cassandra. And I've always said that this is one of those features that Apache Cassandra does better than any other database, in my opinion. That you can have it be aware of like different logical data centers or different geographic regions, so to speak. So if you have an application that you're serving out to customers in like the West Coast of the US, the East Coast of the US, and then maybe in London in the UK, you don't want your users in London having to jump across the pond to where your data center is to make a data call. So what you do is you specify those, each of those three regions, which would be like, US West, US East, and then it's like EU1, or trying to remember what, a lot of them designate the UK as. But the idea is that way your data is close to the application, and you're getting that quick real-time response that your customers need. So here's an easy one for you. What should I use Temporal for?
Sure. So durable execution is a new programming primitive, and it's sort of coding at a higher level of abstraction, where you can be oblivious to faults in the underlying system, whether that be the hardware or the network. And so it's very generally applicably useful. I'd say the easiest way to classify when to use it is when to not use it, and then use it for everything else. So when to not use it is for particularly latency sensitive applications. Again, we're working on this and getting better, but there are certain things that you just need to not save things to the database for. Yeah, so it takes time to write to Cassandra, and and we do that a lot. I guess there are specific use case categories that we particularly shine at, have a lot of users doing, and one of them is transaction management, like moving money, particularly between different partitions or databases, order management, fulfillment, state synchronization between multiple stores, business processes. So generally speaking, a set of linked tasks that deliver a service or a product to a client. One example is Checker uses us for background checks. So there's lots of different steps in the background check. Some of them are automated, some of them are manual. Transcription, Descript uses us for transcripting videos. Supply chain things, any documented business process. And you can sort of abstract that to any piece of code, any function that does multiple steps you can think of as a business process. And if you want that to be reliable, then you can use Temporal. Another category is entity lifecycle. So this is like the loyalty program that I talked about, management of an item or business entity like a user through a lifecycle of events. And you can do inventory management, menu listing versioning is one of our customers uses that, or user management. And then the final category that we have a lot of is operational workloads like infrastructure deployment, CI/CD workflows, data and ML pipelines.
Oh, excellent. Excellent. So another one here for DataStax. So I'm building my app, let's say it's in, Java or Python or JavaScript, how easy is it to connect to Astra DB? Does DataStax have an API integration? What's available? And the answer to that is, first and foremost, we have drivers for most languages out there that have been in the open source community for a while. They're very, very mature. They connect over the the CQL binary native protocol. But on the other hand, when you're using DataStax Astra, we have our own API layer that kind of sits in front of that. That's called Stargate. And you can connect through through Stargate with you can still use the CQL protocol. You can use gRPC. We have a document API that kind of works in the same paradigm as a lot of document databases does. And we also have a REST API as well as GraphQL. So there's many different ways that you can have your application connect up to the database, and you don't necessarily have to go and learn a database domain specific language to do it. All right. So here's one for you, Loren. Loren, you wrote a blog post in which you said that Temporal makes it trivial or unnecessary to implement distributed systems patterns like, event-driven architecture, task queues, and sagas. Can you explain why or how that is?
Sure. So I guess the problem of coordinating between microservices is broad and has lots of different pieces to it. One pattern that has a lot of answers in it is event-driven architecture. And sometimes people just equate that with choreography, but I think more generally speaking, it's anything that's like event-based, like event sourcing or even orchestration is event-based. Using event-based architecture helps you get out of like doing asynchronous request responses, which doesn't work well, especially in failure scenarios. If there's some business process that needs to talk to multiple services to resolve, synchronously calling just doesn't work well or scale well. So instead, you'll write an event to a message bus, or you'll start a orchestrator process or workflow. And I guess in this realm, the big two main systems are choreography and orchestration. And Chris Richardson in his book about microservices basically recommends using orchestration for anything but the most simple of cases, because choreography can get really complex to reason about what's happened. And so like choreography, you instead of calling a service or multiple services, you write or you publish an event to a message bus, and then anything that wants to respond to that type of event consumes it and does something, and maybe publishes another event, etc. So you have events going to the store, and you have things, services that are deployed separately, responding to them, and it's hard to reason about what's happening, to view what's happening, like observability of these business processes as they're happening, or how they happened in the past is hard. So debugging is really difficult. So this is part of why Chris recommends using orchestration. And then once you're in the orchestration realm of event-driven architecture, you have to choose an orchestration engine. And Temporal is basically an orchestration engine that is easy to use and highly scalable and highly reliable. Most orchestration engines are DSL based, where you write, you draw a DAG with diagrams, or you write a JSON or YAML file, like AWS step functions, where you're basically defining the logic in a markup file, and that isn't very expressive. Like you could have like you can have if statements and loops and like go-tos, but it's not as expressive as code, as a programming language, and it's much harder to develop with. It's harder to debug, to deploy, and version, and lots of different things. So one of our big beliefs is that a workflow that you're orchestrating is logic, and the best way to write and debug and maintain logic is with code. So we are a code-based orchestrator with relatively good developer experience compared to the DSLs and the markup language versions. So I guess that's speaking to the event-driven architecture pattern for let's say sagas. So you use a saga when you have multiple services with each have a different data store, and you need to update both of them in sync to be consistent. And you don't tend to want to use two-phase commit, because it has a low throughput and low latency. And so if you need higher throughput, then you use a saga, which is using either choreography or orchestration to update one, try to update one source, and then try to update the next one. If this succeeds, then try to the next one. If that fails, then undo that one, which is the failure compensation. And if it succeeds, then you're done. And you can have more than just two steps, and more different types of failure compensation. And that's really easy to code in Temporal. You can just have a try catch, and in the catch you do the compensation. So that's sagas. Task queues is another common paradigm just in backend async work. So if you have something that might take a while, like so you get a request from the user, and the thing they're wanting you to do might take a while, and it might take longer than you have to respond to the user in like this HTTP request, or it might fail, and you might need to retry this work. Then what you do is once you get the request from the user, instead of doing the work, you put a task on a queue, and then once that task is reliably stored, then you say, okay, user, I'll get it done at some point. And then the async work is being done by like a worker pool. So a good example of this would be your YouTube. You're implementing YouTube, and a user uploads a video. You need to process it in different like file formats and resolutions to then host on your cloud storage place. So the workers would be picking up these tasks and trying to do the work, and if they fail to report in a certain amount of time, then another worker will pick up that, and then once the worker succeeds, it'll say, okay, task queue, you can take this off the queue now. It's been completed. And this is a very common pattern, and it's something that Temporal does for you automatically. So you don't have to write events to the queues. You don't have to be worried about the logic of like taking things off the queue provisionally and then having timeouts and stuff. Every time you call a durable function, every time that function calls another durable function or calls a volatile function or calls sleep, or not sleep, but well, yeah, I guess sleep too. But anytime it does anything, what's happening underneath the hood is another task is going on a queue to execute that for you in like the worker polling on a queue style. So that's done for you automatically. I guess two more quick patterns, distributed system patterns that we fix for or do for you basically are circuit breakers and transactional app boxes. So circuit breaker pattern is you have something user request comes in and it's going to require talking to multiple services to complete. So let's say the user request comes to this service and the service needs to do something and then talk to this service. If this service, the downstream one, is down or like really slow, then this service is stuck with threads that are retrying or waiting. And once those fill up the but it's still getting new requests while these are waiting. So if it takes up a thread per request, then it fills up all the requests and it can't take any more new requests. And this can be a cascading failure where, okay, whatever's calling this one now is going to fill up threads and have resource exhaustion and not be able to take new requests. So the circuit breaker pattern is instead of synchronously calling the downstream service, you do it async and you have a proxy, and then you ask the proxy to do this and to back off exponentially if it can't reach the downstream service, and then report back the result. And that's something that Temporal does automatically for you. And then the last one is transactional app boxes. So it's sort of similar to a Saga in that if you need to do two things at once, if you need to update state in a database and also publish a message to an event bus at the same time, if you're coding that naively, first you'll do that one. First you'll update the database, and then in the next line of code you will send the message. That has consistency issues because maybe the process dies in between those two steps, or maybe the message bus is unavailable for some period of time, and that increases the amount of time that you might crash and lose state. So what you do is you need to atomically do them at the same time, but you can't because they're separate data stores. So what you do is you have a transactional outbox, or also called a transfer queue, that's in the same partition as the state you're updating the database. You also have a queue, and you update in a single atomic transaction, and then you have another process that is polling for anything new on these per partition transfer queues, and if there is, then they try to write it to the message bus, and if they succeed, then they take it off the queue, and if they don't, then it gets retried. Yeah. So
wow.
Those are just some of the many patterns that. So in a transactional appbox case, you don't need to do that with Temporal because the entire premise is that your function might die. So with non-volatile, with durable functions, you can trust that the next step will happen eventually. Just like when you're using the transactional outbox pattern, you trust that eventually that process will take it off the transfer queue and get it to the message bus.
Excellent. Wow, yeah, that was quite a bit. All right. So hey, a couple more here. One, does Astra DB integrate with technologies like Kubernetes and Pulsar? So for that, I can say that, the DataStax Astra Streaming offering is built on Apache Pulsar, and that is a really useful tool, for being able to build up, things like message queues and use the publish subscribe paradigm, and even pipe data between different databases in real time. It's a great tool to have. And then Kubernetes, well, of course, Astra DB is built on Kubernetes. So we really are, helping you take advantage of, being able to split out things like, your compute resources from your storage resources, and to really drive for the best performance on that end. Okay, last one here. How does Temporal fit with a message broker like Astra Streaming? Oh, so real similar to the last one. Okay.
Yeah, so I guess there are a couple of ways to think about how it fits with something like Astra Streaming or Pulsar or Kafka, and that is you can have a consumer responding to events that starts a durable function, and then I guess the main thing to note there is that the method of deduplication we support is whenever you start a durable function, which we call a workflow, you always give it a workflow ID, and that's unique among all running functions. And so if you start a workflow with the same ID, it'll fail. So what you need to do is when you're consuming events, it's usually possible that there will be duplicate events. So you need to deterministically generate a function ID from the data in the event. So if it's something that came from a client, like an order ID, that or item potency token, some kind of client request ID that can go through, and that can be your ID, function ID. But there are other methods, like you could take a hash of all of the data and use that. So that's like on the consuming side and starting workflows. When you are already in temporal land and you want to publish a message, I guess so if it's like a greenfield thing, or if it's like features you're building new, you would probably not publish anywhere else. You would just use like the automatic sort of event sourcing that's built into temporal by just calling volatile functions directly. But assuming you're trying to integrate with something existing that's elsewhere in your system, and that responds to a message on a bus, then you can have one of your volatile functions, which we call activities, publish a message to the bus, and just like all of volatile functions that are called from durable functions, we automatically retry them on failure. So you can be assured that eventually the message will go out on the bus.
Well, folks, I think that does it for all the time we have. Hey, Loren, thank you so much for taking your time and joining me in this session. For any of you folks out there, if you have any other questions, feel free to check out our websites, datastax.com and temporal.io. We both have ways that you can fill out contact forms and get a hold of us. Otherwise, I'm on Twitter at Aplets, and Loren's on Twitter at Loren DSR. So hey, that's it. Thank you all very much. Have a great day.